Now we are going to have a look at charts more in details, in particular 2 types of charts, pie chart first, and then we'll look at bar chart as well. So I'll start with quite simple examples of how to use pie chart using our hypothetical data set. So you got 2 pie charts in this slide. On the top pie chart, you have people not dispatched as cardiac arrest, and you got the subdivision into males and females, basically. So the biggest slice, which is the orange slice, is for females. You got 14 females in this subgroup and 11 males in the subgroup. So the biggest slice is going to be for females, 56%, and the smallest slice is going to be for males. So very simple interpretation here. The same for the other subgroup, people dispatched as cardiac arrest in this case. In this particular situation, we got more males, so 11 males, and so the bigger slice will be for males, the blue slice there, which is about 3/4 of the whole cake, if you want, of the whole pie. So this is just to give you a pretty basic examples of how to use pie charts with our hypothetical data set. Now, let's have a look at bar chart. So bar chart, we got bars instead. So we got vertical and horizontal axis. In the vertical axis, we got percentages. Horizontal axis, we got our variables, basically. So we got gender in this particular case. And the question we are looking at is whether people were dispatched as cardiac arrest or not. And you got no on the left-hand side and yes on the right-hand side. And then for the no, so people not dispatched as cardiac arrest, you got a subdivision in males and females. And for the yes, so people dispatched as cardiac arrest, you got the subdivision into males and females. So it's a kind of two-way bar chart here, because we are considering 2 variables at the time, dispatches and gender. Here you can see that 50% of males were not dispatched as cardiac arrest, and 50% of males were dispatched as cardiac arrest, so the bars have the same size. On the other hand, the majority of females were not dispatched as cardiac arrest, so more than 3/4 of females were not dispatched as cardiac arrest, and just less than 1/4 of females were dispatched as cardiac arrest. And you can see the difference in the size, in the sizes of the bars here. So the orange bar on the right-hand side is smaller than the orange bar on the left-hand side. We're trying to complicate things a bit more by adding more categories. So we are now considering a variable more than 2 categories. In this case, we are using age groups. We got 5 age groups, which go from the youngest people in the data set to the older people in the data set. Here we got a representation of the percentages for each age group graphically. So you will see that, for example, the first 3 age group got all the same percentage, so the bars will be the same, will be of the same size. The 4th age group is the bigger age group in terms of counts, in terms of percentages, sorry. And then the 5th age group is the smallest one, so only 17.5% of people will be in that particular age group. I'll move on to this other bar chart here. Here things are getting a bit more complicated. So what we are seeing here is that we have basically 2 variables again. We are considering 2 variables at the same time, gender and age groups, and you will see bars for each gender for each age group. So for example, if you are just taking into consideration the first age group, so people who are younger than 36 years old, you will see that 5 males are in this particular age group, 3 females are in this particular age group, and the bars will tell you how many males are in that particular age group out of the total number of males. So you got 5 males out of 22. You will see the number 22 at the top. 5 males out of 22 are in the first age group, okay? And that is 22.7% of males falling into that particular age group. The same interpretation for females. 16.7% of females will be in the first age group, okay? So if you add all the percentages for the blue bars, for example, so you take 22.7 plus 18 18.2 plus 22.7 plus 18.2 plus 18.2, you get 100%, okay? And the same for the orange bars for females. Now, I've given you some examples of pie chart first and then bar charts. What I would like to focus now is what's the difference between pie and bar chart. So how do we decide whether it's better to use a pie chart in one case or it's better to use a bar chart in one specific case? The thing you need to focus on, the thing you need to remember is whether you got an order in your categories, right? So if you remember the examples with the pie chart that I was showing you a minute ago, we were considering gender. With gender, you don't have an order. So you can put females on the right-hand side, males on the right-hand side. It doesn't really matter. When you have an order instead, for example, here we got a temporal order. So you got age groups which go from the youngest to the oldest people in the data set. In that particular case, then it might be more appropriate to use a bar chart, because a bar chart will give you this indication that there is an order in the categories you're trying to graphically represent. The same goes with, for example, month of the year. So if you're trying to do some counts for a certain occurrences throughout the year, you might want to represent these counts graphically using a bar chart. So from January to December, for example. When you don't have an order, for example, with gender before, then pie charts might be an option. So in that particular case, you might decide to use a pie chart. If you have an order, then bar charts instead are more appropriate or tend to be more. I'll show you an example of a pie chart, which was taken from a report from the Lancashire Teaching Hospital NHS Foundation Trust. This is just to give an indication when a pie chart might be a good representation of what's happening with your data. So here you got 3 categories: estate maintenance, information technology, medical equipment replacement. And as you can see, it's quite good, it's quite immediate to understand what's going on in this pie chart. So you can see estate maintenance is basically covering more than half of the pie, and then you got smaller slices for the other 2 items there. Now, things might get a bit more complicated when you start adding categories. So another thing you need to remember when you decide whether to use a pie chart or a bar chart, for example, how many categories you are assessing. Here we have, for example, I think 7 categories. And the more you add categories, the more it will be difficult for the reader to understand what's going on in your pie chart, okay? So you will have probably very small slices, and you will have to probably use arrows to indicate that slice corresponds to this particular category, to this particular item. And for the reader, it will be increasingly difficult to understand what's going on, okay? So if you got a relatively small number of categories, then it's fine to use a pie chart, but the more categories you have, then it tends not to be good to use a pie chart, and you might decide to use a bar chart, for example. So these are just practical examples when pie chart might be good or not when we're trying to graphically represent our data.
I'm going to bring us back to the opening question. So we were looking at this study based on cardiac arrest or not dispatched as cardiac arrest. And one of the questions, the question we were looking at was, is the age of the patients not dispatched as cardiac arrest different to the age of the patients who are dispatched as cardiac arrest? Now, I've laid out all of our individual pieces of data points, so all of our participants, and I've split them. You've got your not dispatched on your left and your dispatched as cardiac arrest on your right. Now, are we able to answer that question just looking at the table like that, looking at all of our data? Not really, no. Now, what we need is some way of representing each of those groups. So the group, when I say groups, I mean are not dispatched and are dispatched. We need something that represents that group overall picture, if you like. And what we use is something called a measure of central tendency, or an average. Now, we're going to go through a couple now, as well as some things that come along with those. But the first one we're going to go through is the mean. Now, I'm sure we've all heard of the mean. It's the most commonly used average. And the mean is useful because one of the main things the mean does, or any average does, is it accounts for sample size. So you'll see on the left we have, I need to remember how many there were. Is it 25 and I think and 15? So I think we've got 25 not dispatched as cardiac arrest, but we've got 15 dispatched as cardiac arrest. But the good thing about something like the mean or another average is it accounts for that. So we've got no worries about whether one group is bigger than the other. And to work out our mean, what we do is we add up all of our individual values, and then we divide by how many values we have. So on the left there, for our not dispatched group, our total, so that's each of those ages added together, is 1,359. We've got 25 individual patients, so we divide that number by 25, which gives us a mean of 54, and we've done these to whole numbers just to for simplicity. On our right hand side, we've got a total of 1,113. We've got 15 patients, so we divide it by 15, which gives an average of 74. Okay, so have we answered our question now? We've got an age that represents our group for not dispatched, and we've got an age that represents our group for dispatched. So if we bring back that question, is the age of dispatched different to the age of not dispatched? I think we do have an answer there. We've got 54 for not dispatched and we've got 74 for dispatched. So our group of dispatched as cardiac arrest is older than our group for not dispatched. Now, as I was saying, the mean is a central tendency. It's a balance point, is another way to call it, or an average, obviously, as well. There's the same weight of numbers either side of your central tendency. Now, that doesn't mean there's the same amount. So there could be, in our group of 25, for example, there could only be 5 numbers above that value, and there could be 20 below it. But it's still the measure of the center due to the weight of those numbers, i.e. the actual numerical value of them. And as we said, as we went through there, we've got our calculation here. So we add up all of our total, all of our values to get a total, and then we divide by the number of values that we had to find our mean. And again, yep, it does it corrects for our sample size, which means we could have 100 people in one group and 7 in another, and those means are still going to be comparable and to be able to make comparisons with. There are other questions about, obviously, the balance of the groups there you could go into, but by essence, the mean can be compared. Okay, so we've got our mean. We've got a value now that represents our group, but what it doesn't tell us is a little bit more about that group. How widely spread is my data? How narrow is my data? Are all of my data points sort of alongside that mean and really consistent, or are they really spread out? And I've got a big variety. So what we need is a measure of spread. Now, with the mean comes something called standard deviation, which I'm hoping you guys have hopefully heard about before. So standard deviation pairs with the mean. So the standard deviation is a measure of spread. It tells us how varied our data is, how spread out it is, whether we had if I go back a slide here, we've got a mean of 54, but we've got a range there. Our lowest value is 5 and our highest is 77. And on the right hand side, our lowest value is only 55. So you can already see potentially we're likely going to see a smaller standard deviation on the right and a bigger one on the left, and we'll come back and see if that's the case once we calculate it. So really important point there, it's not a distance from the mean, an average distance, but it is it works like that in the sense of it gives you an idea of how far away on average, quotation marks, but how far away each of your points is. Ideally, or usually, only a very small proportion, or hopefully none, of your values in your group should be more than 2 of your standard deviation away. Now, if I visualize that a bit better here for you, you've got a standard deviation value and you've got your mean. So your mean is your center and you've got a measure of spread. What you're hoping is if you add or subtract 2 of your standard deviation, so you're going to get 2 above and 2 below, vast majority, if not all of your data points in that group should be within that window. There will be sometimes that lie outside of that, and they're what we call anomalies or extreme data values, if you like, or other things you can call them. Doesn't mean you have to not account for those, but it's a good way of just trying to get an idea of what sort of data you're looking at. We're not going to go through the actual calculation for standard deviation today because it's a little bit more complex. So we're going to give you some standard deviations. So we have our same groups here, and what I've done at the bottom there, we've got 2 standard deviations. So we've got 24 on the left and 10 on the right. And just like we thought when we looked at those values, our standard deviation on the right is much smaller than our one on the left. Now, what we want to do is work out if we've got any extreme values in these groups. So we've got our means and we've got our standard deviations. So what we're going to do is we're going to get two values for each one. We're going to have an upper sort of extreme value and a lower. So for our first group, we've got a mean of 54 and a standard deviation of 24. So we've got 54, and then we're going to take away 2 for 24, so 48. And that's going to give us a lower extreme of 6. So that's our mean minus 2 standard deviations. And for our upper extreme, we've got 54 plus 2 24, so 48, all the way up to 102. So our window for our first group is 6 to 102. And what that's going to tell us is if we've got values that are outside that window, we know they are extreme values. Our second group, so 74 is our mean and our standard deviation is 10. So we're going to have 74 take away 2 times 10, so 20. It's going to give us 54 as our lower extreme, and our upper extreme is going to be 94. You can already see with those extremes, that's a much narrower window in that second group, which also means you are potentially more likely to get an extreme value, but then it's narrower because the data is narrower. So we've got our values in there. I've highlighted any values that were beyond those extremes, and you'll see that on the not dispatched group, we've got 2 that were below 6. So we've got 2 values of 5, and on the right-hand side, we've got none. Now, that doesn't force anything. It doesn't mean anything too significant, but what it does mean is you can say, oh, well, we've got much more spread data because our standard deviation is a lot higher, and we actually have 2 extreme values in there of 5 in that group. Now, the mean is brilliant and it's used all the time, and standard deviation pairs alongside it. But sometimes the idea of that weight either side of your mean, that's the whole point of a mean, it's about weight. What that means is if you have very extreme values, it can really throw off a mean. So if I use an example here, we've got 11 people who've won on the lottery. We have one person has won £30 million. We've got one person's won 200,000, 100,000, 30,000, and then 7 people, have won £10. Now, if we calculate the mean for that, so we add up all of those monetary prizes and we divide it by the 11 people, the average, the mean, is £2.757 million. That's not really a very good representation of the average winning of those 11 people. Only one person earned more than that. Everybody else won below it, and nobody else was even close. All of those 10 people below that value weren't even close to that 2.7 million. But due to the fact that weight mean is a calculation of weight, you've got 30 million dragging up that mean to 2.7 million and everything else leaving it behind. So we need something that's going to measure our center differently, and we're going to use a median. So again, hopefully we've all heard of the median. The median is middle. It means the middle number. And just like we added all our values together in the last one for the mean, what we're actually going to do here is going to put all our values in order. So from smallest to largest. And I've done that for us here on the left and the right. So we have our not dispatched group, all 25 values listed in order, and then same with the dispatch. Now, to find our middle value, there's a couple of ways to do it. With groups that aren't massive, so for example, if you've got like this, it's 25, or if you're working with a group with 15 values in, I quite like to do a visual way, which I think you often learn in school as a kid, which is you kind of cross off the extremes each time, keep going until you're either left with 1 or 2 numbers in the middle. If you're left with 1, that's your median. If you're left with 2, you're working out the value between those 2 values. The other way, obviously, we wouldn't want to do that if we had a group of 250 odd people in. We wouldn't want to we'd be crossing all day. What we do is there's a calculation to work out which value you need, which is n plus 1 over 2 is the calculation. Now, n is the number of people in your group, and then plus 1, so you add 1 to it and then halve it. So for example, we've got 25 people in our group here on not dispatched. So our n is 25. If we add 1, that's 26, divided by 2, that's 13. So we're looking for the 13th value in our list. So if we go down 1, 2, 3, 4, I know you can't see my mouse, I realize, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 64. Perfect. And if we'd crossed out, we would have got the same value. The one thing to note about that calculation, if you have a even number in your group, so if it was 26, you're going to have 26 plus 1, that's 27, divided by 2. That's going to give you 13.5. Now, what that means, that's the same way that when you cross out, you get two numbers. It just means that we need the value that's between our 13th and 14th in our list. Does that make sense when you're doing that calculation? Great. Okay, so we've got our two medians. We've got 64 on the left and 76 on the right. That's great. It's the same as the mean. We've got a higher one in the right. That's suggesting we've got an average higher age in our dispatch group to our not dispatch. Now, alongside our median, we also need another measure of spread. Now, we can't use standard deviation because that's paired with the mean, and we want to use something that works well with a median because it's calculated differently. And what we use is interquartile range. Now, our median is our middle value. That's what we know. It's the middle in terms of when they're all in order. For our interquartile range, we're now going to need the middle of our two halves. We're going to need our quartiles. Our lower quartile is going to be that middle number between the first number and the median, and our upper quartile is going to be the middle number between our median and our highest value. The interquartile range being our upper quartile minus our lower quartile, the range between those two quartiles. Just for reference, obviously the range itself, so just the normal range would be your highest minus your lowest. That's the full range of your data. Okay, so let's have a look at our data then. So we have in our left group, again, you can do it by crossing out, or you can do it through the calculation. So we have a lower quartile of 35. So we had 35 and 35, we had two numbers, but since they're the same, that means our lower quartile is 35. And our upper quartile, same with the 74, is 74, which means our interquartile range is going to be 74 minus 35, which gives us 39. That's our measure of spread. On our dispatched group, we have a lower quartile of 66 and an upper quartile of 82. Our interquartile range is therefore going to be 16. Now, just like we had with the mean and standard deviation, we've got a higher mean in our dispatched group, which suggests a higher age. And we also have a narrower measure of spread, so a smaller standard deviation and then a smaller interquartile range. So we know that those two different ways of calculating our average and our spread are still giving us the same answers, which is obviously always really good. Okay, kind of linking into what we were doing before with displaying data, something that's unique to medians and interquartile range is something called box plots. So we've got our two results there that I've taken from the bottom of that last table. So we've got all of our quartiles, our median, and our interquartile ranges for our two groups. What I've done here is we've got two box plots to represent that. Now, a box plot is really useful for this stuff because it actually shows you every single bit of information that we've calculated, not just one or two that we choose to display. We've got on there our median, which is our thick line in the middle. We've got our upper quartile and lower quartile, which are the edges of the boxes. We have our maximum and minimums, which is the end of the whiskers. And then your interquartile range is the height of the box, if you like. So we've got every single bit of information in there, and it also is a visual representation. So now, we've said there's a higher average range, and we've said the second group was narrower. We can visually see that now. So we've got that thick line on the right is higher than the thick line on the left. That's our medians. And we can also see that box is much, much narrower on the dispatched group than it is on the not dispatched. Okay. So what have we gone through there? We've gone through the mean, we've gone through calculating the median, and we've had a look at two measures of spread that link with those. So standard deviation with mean and an interquartile range with the median. We also briefly had the range on that box plot as well, which I mentioned previously. And I can't stress enough, mean goes with standard deviation, median goes with interquartile range, minimum maximum, so your range goes with anything. When you're going through, maybe you're reading through a study, you will always find those pairs together. So, and also if you are doing some summary stats yourself, if you're calculating means, you must always calculate a standard deviation. You can do that on, there's online calculators available. And the reason for that is when you present data, for example, if you're presenting a mean in a paper, you will want to be putting, okay, my mean is 17, and then you'd put plus or minus 12, and 12 is your standard deviation, 17 is your mean. So mean is always presented with standard deviation, the same again with median with interquartile range. Okay, so these are our descriptive or summary statistics. It doesn't matter how many times I say that, I will always mess that word up. And it's what we use to describe data. You can use it to infer further things, which is a separate topic in itself, inferential statistics, but it's a way of summarizing what's in front of you to have maybe one or two values that represent a full data set of 1,000 people.
When you do your own analysis, you will deal with different types of data. There are two main categories. One is numeric or quantitative data, which again subdivides into continuous data and discrete data. What I mean with continuous data. Continuous data is things you can measure. You can measure age, you can measure BMI, cholesterol level. Discrete data instead is things you can count. So you can count the number of incontinence episodes in 1 week, the number of symptoms. You can count the number of siblings in your family, for example, and that will be a whole number. It can't be 2.5 sisters in your family. You either have 2 or 3 sisters. That's what we're talking about, discrete or whole number. On the other hand, we got categorical data. The type of data we saw today, like gender, for example, is a categorical data. You will probably see binary nominal data, in particular things that are in 2 categories, male, female, smoker or no smoker. So you'll have categorical nominal data when you don't have any order in your categories, and you can position things as you wish, as I was explaining before with the pie chart, for example. You might have more than 2 categories. So if you think about marital status, ethnic origin, you will have more than 2 categories. And again, you don't have a particular order there. Another type of categorical data is ordinal data, when instead you have an order. Age groups, social class, agreement, like this Likert scale questions. These are all type of data where you do have an order. Why is it important to understand the difference? Because it will have an implication on the way you describe the data. So if you got for example, nominal data, you can use pie chart. If you got ordinal data, you might want to use bar chart because you got an order. And it will have an implication on the way you analyze data. If you got age, you can calculate mean, standard deviation. If you got gender, it doesn't make sense to calculate the mean for gender. You will only calculate percentages for males and females, and that's it. So understanding what type of data you're dealing with will have, is good in terms of understanding what kind of description and analysis of data you can carry out.